Hello, and welcome to Backer Breaks It Down. In this episode, we are still working with segments related to a circle. This time we're focusing on those segments created by two secants. Okay, so secant-secant power theorem. Let's check it out. So if two secant segments are drawn from an external point to a circle, then the product of the measures of one secant segment and its external part is equal to the product of the measures of the other secant segment and its external part. So simply put, you've got two secants. Well, focus on one of them at a time. Write one side of your equation, the whole secant times its external part. Okay, so that's what you have over here. The whole secant is given by a plus b. The external part is a. And then this is equal to the other whole secant and its external part. So that's where they're getting the c times c plus d. Okay, so I need to know the external parts and I need to know the whole secants. So like here in the apply it, this bottom secant, like the whole thing would be x plus 5. And then the secant on top, the whole thing would be 9 plus 6, which is 15. Okay. So writing it out, I have like the whole secant, which is 15, times its external part, which is 6, is equal to the whole secant, which is x plus 5, times its external part, which is 5. And then I'm just doing this math. Okay, so 15 times 6, that gives me 90. So 90 is equal to 5x plus 25. And then I'm just doing some algebra to solve this. So 65 is equal to 5x, thus x is going to be 13. So that one was pretty simple, right? So let's do it again with some algebra, okay? So in number 3 here, I am working with two secants. The one on top, the entire length of it is going to be x plus 5. And then the one on the bottom, the entire length would be 12. So then I just use my power theorem to set it up. So starting with the one on top, I've got the whole secant, which is x plus 5, and I'm multiplying by its external part, which is x. And then for the bottom secant, I've got the whole secant, which is 12, and I'm multiplying that by its external part, which is 3. So then I got to clean this up a little bit. So I'm going to distribute on the left-hand side here, and I get x squared plus 5x, and this is equal to 36. And then since this is a quadratic equation, I have to get it equal to 0. So I'm going to subtract 36 from both sides, and then I'm ready to factor. Okay, and this one should be a nice easy one to factor because it's just x squared. And so naturally, I've already done all that. So the factored form is the quantity x plus 9 times the quantity x minus 4. Algebraically, there are two solutions of negative 9 and 4, but the negative 9 doesn't make sense. 4 does. Okay, so I do have one more example for us to check out. And you'll notice that there's two things that they want us to find. They want us to find x and y. So we might have to use more than one of our power functions. Okay, well, our power theorems. So let's kind of like look at what we have here. So that 12, like I'm looking at the 12 at that segment and I'm like, well, that's a tangent. So the fact that like they gave me that tangent, it's like, ooh, I might want to use this power theorem that says the tangent squared is equal to the secant times its external part. Okay, so let's look at that secant. Let me highlight that for us. This is that secant that it would have a relationship with. Okay, and so I believe that smaller segment is 3. Okay, right, and then you've got y and 6. So we kind of have to be like a little bit careful here. So 6 is definitely the external part of the secant. When it comes to the whole secant would be y, and then 3 plus 6 is 9. Okay, and so I'm ready to figure out what y is. So I would have the tangent squared is equal to the whole secant of y plus 9 times its external part, which is simply 6. So I am able to solve this equation pretty easily because it is simply like a linear equation. So it does make things a little bit easier for me. So I end up with 90 is equal to 6 times y, thus y is equal to 15. Okay. But what about x? So what I notice about x is that it's part of a chord that's been chopped into two smaller segments. One of them's x, one of them's 2. And so like the other chord in this problem, because we've got that chord power theorem, would be this one here made up of 3 and y. So like I can create an equation where I have the product of the segments of one chord equals the product of the segments of the other chord. So I have 2 times x equals 3 times y. Now I know what y is. Y is 15, so I should like make that substitution. So I'm going to have 2x is equal to 3 times 15, which is 45. And then if I do the math, I get that x is 22.5. So I definitely couldn't have started with my 2 chords because there were 2 unknowns. Like the fact that the tangent segment jumped out at me that was kind of good because that's where I needed to start, was with that tangent segment. Okay. But this video was primarily on that secant-secant power theorem, which basically says the whole secant times its external part is equal to the other whole secant times its external part. And that's how Backer breaks it down.